Hello, my name is Arya Tschand, and my research project deals with developing an intelligent and affordable autonomous irrigation system specifically intended for water conservation in developing nations. The global water crisis affects an estimated 2.8 billion people worldwide, and, as the graph depicts, a majority of those most affected live in developing nations in South Asia, the Middle East, and North Africa. The largest cause for mass water shortage is agricultural water wastage, and the United Nations estimates that over 42% of global water consumption is wasted through overwatering and leakages. In my recent visits to India, I witnessed this problem firsthand, and this experience inspired me to carry out my research project. Current irrigation infrastructure in developing nations is primitive, but it is impractical to develop efficient irrigation methods that completely replace existing infrastructure. Instead, this project aims to develop an affordable autonomous irrigation system to integrate directly into existing infrastructure and utilize artificial intelligence to minimize water wastage. The system is designed to minimize water wastage while maximizing crop growth efficiency, while operating as completely power self-sufficient, scalable, and standalone from a networking perspective. The student researcher predicted that the constructed system will be significantly different and more efficient than the current, more manual and wasteful irrigation methods. All assumptions to allow for maximum data accuracy were monitored and never found to be false at the conclusion of the experiment. Here is a full list of all the hardware materials and equipment utilized for the irrigation system construction. Here's a list of all the software materials and equipment utilized for the irrigation system functionality. Here's the procedure for constructing the data collection drone and irrigation micropiece. All parts of the drone were purchased separately for affordability and attached, soldered, and screwed together by the student researcher. The irrigation micropiece and 3D model was completely constructed and printed by the student researcher for maximum precision. Here's the procedure for programming the artificial intelligence neural network. Instead of utilizing pre-built and trained neural network models, all neural network programming was done by the researcher from scratch. While some accuracy was sacrificed, this allowed the network to be formulated and trained specifically for the experiment, improving learning rate and minimizing outside error. A rotational irrigation mechanism was constructed to collect crop data and test the strength of correlation between HSV crop color and ideal irrigation volume when utilized by an artificial intelligence dynamic linear regression algorithm. A growth cycle of 12 plants was completed by planting the seeds, utilizing the mechanism for watering, and collecting necessary data 5 weeks later. On this slide, you can see a short clip of the mechanism in motion. The secondary irrigation system is designed to be practical, scalable, integrate into existing infrastructure, and operate as a standalone network. In this diagram, you can see the system architecture specifically indicating communication between components. All components within the dotted box communicate via local area network, or LAN, for fast and reliable communication without the need for existing network infrastructure or internet access. On this slide, you can see a diagram depicting the flow between nodes of the 5-layer recurrent neural network. Inputted data is activated using logistic and hyperbolic tangent functions and passed through regression regularization algorithms to calculate aggregated node weights. Essentially, the predicted irrigation volume is adjusted systematically in proportion to the correlation between crop color and irrigation volume. All code was programmed from scratch in Python. Here are all of the fundamental dynamic linear regression, node weight regularization, backpropagation loss calculation, and self-optimization functions used by the neural network and their derivations from standard artificial intelligence formulas. Each unique formula was derived by the student researcher to adjust to the unique inputted dataset, designated optimization methods, and final output. Therefore, while the network may not perform at maximum accuracy, they are derived for maximum precision to this unique project and its input outputs. Here's a diagram of the computer vision usage of the neural network to calculate the average brightness adjusted HSV crop color. K-means clustering algorithms were utilized to isolate the pixels within the crop leaf and adjust the image brightness to standardize the color regardless of time of day. The irrigation micropiece is constructed to integrate into the water-carrying pipe irrigation infrastructure. It is capable of irrigating crops with dynamic irrigation volumes and is power self-sufficient from the power induced from the water current. The irrigation micropiece is a combination of an Arduino Nano-based circuit with an ESP8226 Wi-Fi module for LAN communication and a 3D printed shell. When combined, it serves the desired function at a minimal per unit price. Flux and EMF calculations were performed to test power consumption to usage, yielding a conclusion of complete and scalable power self-sufficiency at an excess margin of 25.8%. This 3D graph depicts power consumption in respect to water flow rate and amperage of the current. Using turbine-specific derived formulas, the difference between the required power and intersection of graphs or the produced power indicated power self-sufficiency. Finally, the field analysis drone was constructed to collect crop and environmental data to feed into the neural network as data points and uses radio frequency identification, or RFID, for relative location instead of expensive and unpredictable GPS. All components of the field analysis drone were purchased individually to minimize cost. Each structure and electrical piece was connected to one another via hot glue, solder, or nuts and bolts to create the final drone. A Raspberry Pi circuit was constructed and attached to the drone to collect the data points with various sensors, access its relative location with an MFRC522 RFID module, and send all data back through a LAN. Here's a short presentation of the irrigation system functionality.
Now, for the user, there is a live feed presented, which allows them to not only monitor where the drone is, but also what it is doing at the current moment. Now, if I put my finger over, you'll see that the live feed will update and return back to normal. Now, I prepared a full demonstration program to demonstrate how each component is connected with one another, as well as how each component operates. All a user would have to do to begin the program is click on a button on their iOS device, and what this allows them to do is tell the system to begin collecting points, analyzing points, and executing them. Now, right now the drone is asking for an RFID tag, and what this allows it to do is access its relative location in respect to the farm. Instead of using GPS location as an absolute location, the system uses RFID tags cross-referenced with a server to provide an XY coordinate, allowing the system to operate as a standalone from a networking perspective. Now, each irrigation micropiece has an RFID tag on it, and when scanned, you'll notice that it recognizes it, cross-references it, and converts it to an XY coordinate. Now, once all the data points are collected, you'll notice that the irrigation micropiece will adjust, and what this allows it to do is adjust the dynamic irrigation volume running through, going towards the plant. Now, as you can see on the computer, which is handling all of the server requests, there is not only base64 images, but also requests from the device and the irrigation micropiece. On the monitor, you'll see, which is reflecting the operating system on the drone, there is image commands running through the shell, as well as data collection commands.
At the conclusion of the experiment, an empirical and simulated dataset were collected. Here, you can see the empirical dataset along with the summative data table. These graphs of the empirical dataset and statistical analysis indicate that the machine learning irrigation approach was 68.8% more efficient than human watering, an extremely significant margin that can have massive implications at the large scales. Furthermore, simulated data from the neural network indicates an extremely fast learning rate to minimal error. Basic regression and function derivations indicate that error drops over 43% within the first growth cycle and approaches 1% error and water loss by the second growth cycle. The findings of the experiment were extremely significant and support the alternate hypothesis. After successfully constructing, programming, and connecting each component of the autonomous irrigation system, the researcher filed a provisional patent and utility patent from the U.S. Patent and Trademark Office, protecting the artificial intelligence software, neural network algorithms, its implementation into an autonomous irrigation system, and the specific hardware constructed for the system. Overall, because of the strong success of the project indicated by multiple statistical analysis measurements of data, it has tremendous potential to help people worldwide affected by the water crisis. In future study, I not only hope to enhance the irrigation system by improving image analysis by using red edge and near-infrared imaging and increasing communication speed and capacity with 5G technology, but also plan on implementing the system in a real farm. I feel that this project has the potential to help people who rarely benefit from technological advancement and hope to implement it in a developing nation where it can have a substantial positive impact. If you would like to view additional resources or project source code, patent documentation, this presentation, or anything else, please scan the corresponding QR code or contact me. Thank you for spending the time to judge my project during the coronavirus pandemic. It means a lot. Thank you.